My name is Uttam Thakur, and I work with Professor Bill Sanders. So UCAS is an anomaly-based IDS for detecting account compromise, and it's used for VPN compromise right now in a university setting. And we've extended this work into the cloud domain, and we'll be demonstrating that work today. So UCAS extracts features from collected logs and looks for anomalies in the usage. So the important question here is, what is anomalous? Now, normally an administrator has to supply this information manually. So as the attacks change, the admin would need to update these features manually as well, which isn't feasible. And we're also assuming that the admin knows what constitutes a compromise ahead of time, which may not necessarily be the case. So UCAS alleviates the problem by using a machine learning to detect from previous logs what constitutes a compromise. So once we run UCAS, we get a list of compromised accounts. And unfortunately, in many domains, though, we need to be able to understand the consequences of a compromise relative to some security policy. So we have a security policy rule validator that examines the extracted features for each of the compromised accounts and checks for violations. And so you might ask, why go through the process of detecting compromised accounts at all? Couldn't we just perform the security policy validation directly against the logs? Unfortunately, that's not always possible. And the reason for that is that, here's some example logs. As you can see, they're extremely verbose and often include many false positives. So we can't just run the security policy validator directly against these logs. It doesn't scale. Plus, detecting compromise is often complex. So we can't just evaluate the events in isolation. We may need to correlate log events from multiple logs across large timescales. So we really need UCAS to detect the compromise before we can delve deeper and validate security policy. So today we're going to show you a prototype for a mechanism by which practitioners can detect account compromise and evaluate the compromise relative to some confidentiality policy. And in our case, we're using a Bell-LaPadula policy. So in our scenario, the Air Force is running a Hadoop cluster, shown here, that's processing data from UAVs. And the different UAVs are working on different projects. Let's call them Project A and Project B. And our security policy lattice shows that data for different projects should not be able to be communicated across the clusters. But the nature of the cloud is sort of at odds with the security goals. Because in our example here, there's a common set of job tracker and task tracker nodes that are used to process data and store data for both projects. So task trackers 1 and 2 are used to store data for Project A, and task trackers 2 and 3 are used as data nodes for Project B. So since the VMs are shared by the clusters, they're at a high privilege level because they both process the data for both projects. An alternative to this would be to separate the infrastructure for Project A and Project B. But the more we do this, the more we defeat the benefits of using the cloud. So we really need to be able to monitor violations of security policy with co-tenant resources. So we assume that there's a centralized logging for this cluster. So let's look at some of the logs now. So here we have some SSH logs, and we can see that there are multiple failed attempts for client 1 SSHing into task tracker 1, and then finally there's one successful attempt here. So UCAS uses this information to detect that there is a potential for account compromise. And this shows an example of using a number of brute force attempts, brute force SSH login attempts as a feature. And this is just one of multiple features UCAS could use. So after we detected this account compromise, what does it mean for our cluster? What does it mean for our security lattice? So this is where we run the security policy rule validator. And when we do so, we find that cluster 1, all of cluster 1 could potentially be compromised. And this is because the account that client 1 compromised has access to all of these resources. So that means that any of Project A's resources could potentially be compromised. Now, another thing that we might want to enforce is isolation as defined by our lattice. So in our case, Project A and Project B should not be able to communicate. So assume some time passes and we get some Hadoop logs. So UCAS detects that client 1 is using a compromised account, using some classifier trained on previous data. So when the security policy rule validation is run, we find that client 1 is using cluster 2 to process its data. And this is a violation of our lattice because client 1 should only have access to Project A's data. So we can see that here, and this is evidenced by the logs, we can see that client 1 is attempting to use job tracker on cluster 2 to process its data. So this could allow client 1 to potentially gain access to sensitive information or hog resources or disrupt the operation of the UAVs using cluster 2, which could be performing critical applications. So in this case, we're using the submitter of the requests and MapReduce job logs as features in our learning. And we may not know the attacks in advance, but UCAS is able to determine, based on previous logs, what an account compromise might be. And then once we determine that, we can use our knowledge of security policy to determine the actual violations that take place and take necessary steps to mitigate the attack. So in conclusion, our anomaly-based IDS allows us to learn anomalous behavior without any manual setting of weights. And we showed a prototype in which practitioners can evaluate potentially compromised accounts relative to confidentiality policy by looking more closely at the features that led to the account compromise in the first place.